Okay. All right. Now, liquids and phase changes. So first of all, how did we come to know that there are the intermolecular forces that exist between the particles? So this all dependent on the properties of the substances or the properties of substances in different substances in phases, in different phases. Okay, so here we have the solids where the particles are very close, okay, very close, and they are in a very nice order, strong attraction, and there's a definite shape, definite volume, and the intermolecular, the attraction is very strong, so the particles are held together strongly. So that's the solids. Liquids, the particles are more mobile, less intermolecular attraction, so the particles are far away. But gas, we already know that they are very, very far away. Okay, very far away. So solids, liquids, and gases, first differences in the arrangement of particles. Now, secondly, how did we know that these particles were arranged? So for example, look at water. Water as a solid, which is ice, for example, and this is water in a liquid state, which is just plain water as we see or we know. And then here is this water in the gaseous state, which we know is a steam. So I'm going to just put it as water vapors. Okay. Now, first thing is the heat of fusion. This is the enthalpy of fusion. Fusion. This is the heat of fusion. Heat of fusion. Heat of fusion is the amount of heat that is needed to convert the water from the solid state to water in a liquid state. And what is that value of that heat? That delta H, and we call it FUS, is equal to, that's the heat of fusion, is equal to 6.02 kilojoules per mole. Okay, so that is the amount of heat that is needed for 1 mole. That is 18 grams of water in a solid state, ice, 6.02. So this small amount of heat is needed. 6.02 kilojoules for 18 grams is not enough. Is like not much of a heat. So a little bit of the heat is needed to dismantle the structure and make it into this breakup. Okay, so that tells us one thing. Next thing is we have this another thing, which is delta H of vaporization. That is the heat of vaporization. So what does the heat of vaporization do? The heat of vaporization is the amount of heat that is needed to convert the water in its liquid state to water in its gaseous state. And how much is that heat? That is delta H VAP. So these are the common, short terms we use. So heat of vaporization in this case is very large in comparison, 40.7 kilojoules per mole. Okay, so we see that it's the water is still the same, but the amount of heat that is needed to dismantle the solid to a liquid is much less than the amount of heat that is needed to break the liquid to make a liquid to a gaseous state. That is like about roughly 7 times more. So there has to be something, some forces inside that are holding these particles together more strongly in the solid. So what do we call them? How do we know about them? Same thing with the liquids. Those forces are there, but less. So the one way of knowing them is the heat is one thing. Next is look at, this is one piece. Next is look at the density. So this is one part. Next is density. Now, density is grams per milliliters if it's a liquid for liquids, and the grams per centimeter cubes for solids. So now look at the density. Now, densities are, regardless whether it's a solid or liquid, doesn't matter. They are also temperature dependent. Temperature dependent. They depend on the temperature. Okay. So we have here the density of ice. So in other words, let's just do water in a solid state. This is water in a liquid state and water in the gaseous state. So what is the density of water when it's in an ice state? So at 0 degrees Celsius and 1 atm, this is our standard conditions, the density of water in the ice state, in the solid state, is equal to 0.9168 grams per centimeter cube. Okay, that's fine. Let's look at the density of water in the liquid state. So at room temperature, obviously, the water is going to exist as water, the liquid water that we know, and 1 atm, so it's at 25 degrees Celsius. The density of water in the liquid state is equal to 0.9971 grams per milliliters. So not much of the difference in comparison. But now look at the density of water in a gaseous state. So in a gaseous state at 400 degrees Celsius, that's when the water is like really, really boiling, and 1 atm, that's a normal pressure. The density of water in the gaseous state is 3.26 into 10 to the power -4 grams per. So since this is a gas, it can be anything, grams per milliliter. Okay. Now we see a huge difference. This is a minor difference, 0.91 and 0.99, but this is huge. This is like significant difference in the density. So that points out again that there has to be like some forces that are responsible for these differences in the density values. Next is, let's look at the compressibility. Now compressibility is when you put the pressure. So compressibility means like when you put pressure on something and you compress it. So pressure from outside. So what is the response when you put the pressure from outside? So a response to the pressure from outside. Okay. So let's look at this now. Here we see that in this case, okay, once again, when you take a solid, so water in its solid state, which is the ice, water in its liquid state, and water in its vaporized state, gaseous state. Okay, so here we see when you put the pressure on ice, so this is the ice, a cube of ice, what is going to happen? What do you expect could happen? Putting a pressure on ice. What would happen if you put the pressure on ice? What could happen? Imagine and tell me what would happen. Melt, okay. Some of it could melt from friction, yes. So if you put the pressure, I mean, it can either melt, or it can even break, right? Either melt, and melt also, melt like it melts a little bit from the top and melt, or it can break. Any of these things can happen. All right. So because ice is at 0 degrees Celsius. So at 0 degrees Celsius and our normal pressure, at 1 atmospheric pressure, our normal pressure, we see the density of ice is 0.9168 grams per centimeter cube. This is our normal atmospheric pressure. But if you increase the pressure and you can increase the pressure to whatever magnitude, like largest pressure. If you increase the pressure, we see that there is a very small change in the density, small change in the density of ice. Okay, not much happens. Same is the case. Look at the water. Here, if you put the pressure, what would happen on a liquid water? What would happen on a liquid water if you put the pressure? What might happen? Just guess. Yeah. Guess here. But what could happen? Not much, right? It can spill off. Yeah. So it can spill off. So what happens here is that you have a density at 25 degrees Celsius, okay, and again 1 atm, our normal pressure, we see that the density does not change much. So the density of water in the liquid state remains 0.9971 grams per milliliters. And when you change it, let us say the pressure, when you increase the pressure to, let us say 1065 atm, now that's a lot of pressure, 1,000 times more. We see that the density of water in the liquid state doesn't change much. It just becomes 1.046 grams per milliliter. So you see here we see the density is 0.99 and 1.46. So not much difference, a little bit. However, look at the pressure. Pressure is 1 atm. This is 1,000 times more. So even with 1,000 times more, the pressure, the density doesn't change that much. It doesn't change to like 1,000 times. So that tells us that the particles are very compact in both liquid and the solid state. But now let's look at scenario with the gases. So here we noticed earlier that at 400 degrees Celsius and 1 atm, the density of the steam, right, water in its gaseous state was 3.26 into 10 to the power negative 4 grams per centimeter cube. Okay, but you're not, okay, it's in the first case you did it only 1,000 times, but here let's just do it only 200 times, like roughly. So if you increase the pressure, that's the pressure increase to 242 atm, 200 times more. The density of water in its gaseous state becomes 0.157 grams per milliliters. Okay, so we see that the density in this scenario, there is quite a huge variation. 1 atm, 1 to 200, like 200 times more. But we see here that this is a very small number, and then it changes to 0.157. So this shows that these particles, the density has changed significantly. So small, so in other words, the conclusion is small change, comparatively, small change in pressure, but larger change in density in the case of, in this scenario here, okay, in the case of the water in the form of like it's steam or vapors. So that tells us that gives us insight into these forces, first of all. So this was the origin of our understanding when we understood the properties of the substances, and we said, okay, something has to do with these particles. Now there's another interesting concept. Look at that. Intramolecular and intermolecular. See, we don't know, we cannot see these atoms and molecules, but, oh, sorry. but we have to make deductions, conclusions from these experiments. So intermolecular forces. So these are the two forces that exist in the substances between the particles. So what is intramolecular? Intramolecular forces is within. Let me write this in a different color. Is inside. These are inside the particles, inside the bonds. And the intramolecular is outside of the particles. So that's the difference. Okay, now let's look at this. For example, you have 1 mole of water. 1 mole of water is equal to 18 grams of water. Now, you take this 1 mole of water and you calculate the heats now. You take water, okay, in the form of a liquid, you heat it, it becomes water in the form of a gas. That means you are vaporizing it. So the energy that is needed, to vaporize 1 mole of water is equal to 40.7 kilojoules. Okay, so for 1 mole of water in the liquid state. So basically, what is happening is that only there's a change of state, but the actual composition is not changing. So this is scenario A. So when we supply 40.7 kilojoules of heat, we see there is just a small change in state. But let's look at this water, and you continue to provide heat in the liquid state, and then it turns to a gaseous state and whatever different states. So what happens is you heat it. What happens is this hydrogen and oxygen bond breaks, and we see that two atoms of hydrogen are released. 1 atom of oxygen is released. So here, the energy needed to break. Now this is actual breaking happening to break the oxygen and hydrogen bond, in 1 mole of water is 934 kilojoules. Okay, so that is the bond energy actually. So this energy is different from this energy. So this is something they observed, that, if the amount of energy that simply brings the transformation, that is just a, it's just a physical, that can just a physical change. So this is called the intermolecular energy. The intermolecular is A. This is the A is the intermolecular. This is the energy that is in between the hydrogen and the other hydrogen. The water and the other water. So this water and this water. Simply, if we want to dismantle their structure, we just need that much. So intermolecular energy is the intermolecular forces rather that are holding it, just holding the structure together. So that is less than the other one. So A is so let's just put this here. A is less than B. So intermolecular forces are less than the intramolecular forces. So that those intramolecular forces have changed the identity. So this is a chemical change only, whereas the intermoleculars just call the physical change if those forces are disturbed. So that's the, Discovery of intermolecular forces, how they were discovered. Okay, so with that said, now we understand that intermolecular is, we are going to now only focus on intermolecular. We've been, in your previous chapters, you've been looking at intramolecular. You've been looking at, bond energies and, all these enthalpies of formation, all those Hess law, all those things you did. That was all intramolecular. This chapter, we are focusing on intermolecular. So intermolecular IMF. Okay, 3 types. One is dipole. Next is London dispersion. Now, London, your book is just talking about dispersion, but really this is London dispersion, or these are also called van der Waals. So London dispersion forces, and these London dispersion forces is also called LDF. And this LDF, the other name of this is van der Waal, VANDERWAALS, van der Waals forces. Now, besides London dispersion and van der Waals, which is basically the same, these are the same, there is also simply called dispersion forces. Now, dispersion forces are, we'll look into that. And then there is hydrogen bonding. So for hydrogen bonding, I'm going to just use the word like HB, bond, short form. Okay, so these are the different types which are also responsible for the properties of substances. And those properties are molecular weight, densities, melting points, boiling points, and so forth. Okay, now let's look at. So the kind of questions, and I'm going to just put it here, that on the exams, there are going to be some questions that relate to, identify the intermolecular forces in these molecules, or why does this molecule have a higher boiling point or a higher melting point, or why is the density and so, those things. Okay, so let's look at it first of all. First is, and this is first, properties. Second, third. Okay, so dipole. Di means two, pole means, poles. So in molecules where there is a induced dipole, because one atom is more electronegative than the other. So for example here, hydrogen attached to X. Now what is X? X is equal to fluorine, chlorine, bromine, iodine, right? It can also be oxygen, it can also be nitrogen. X can also be these two. So these upper ones are called halogens. Okay, halogens, or oxygen and nitrogen. Why? Because these guys have very high electronegativities in comparison to hydrogen. Very high electronegativities, En, okay, in comparison to hydrogen. Now, what's the deal with hydrogen? Hydrogen has a very small size. So small size and less electronegative. So that's one thing. So what happens with that? So this is what happens. Here is this hydrogen, and this is, let's say, chlorine. So we see that chlorine, being highly electronegative, pulls the electron clouds towards itself. And so the whole electron cloud, electrons that were being shared, right? Electrons were being shared between hydrogen and chlorine, but chlorine pulls that shared pair of electrons also towards itself. As a result, chlorine gets a delta negative charge, and this hydrogen gets a delta positive charge. All right, so this is induced dipole. Induced. dipole because of the nature of chlorine. That's what it, chlorine is like that. If chlorine was there, nitrogen was there, same story. Fluorine, same story. It's just whichever is the one with more electronegative, it is going to happen. But okay, fine. How do they arrange or stack? So what happens is, here is this hydrogen with its delta negative charge, and here's the chlorine with its delta positive, chlorine has a delta negative, delta, this is delta. Delta means very small or slight. So this is a slight charge. The bond is not breaking, the bond is still there. Okay, so hydrogen has a delta positive. Now, here is hydrogen is going to be near chlorine, and here every chlorine is going to be near a hydrogen, and every hydrogen is going to be near chlorine. So when they stack or they are arranged with each other, this is how they look like. So positive of one is close to the negative of the other. And this is basically a very weak electrostatic attraction. Their arrangement is like that. They're not connected to each other. They are not they are not bonded, but it's just the attraction is there between positive and negative of each other. So these remain, connected in this network. And this is pretty strong network in comparison. Now, if you remember the lab you guys did in which you synthesized hydrogen gas, right? Determining the value of R. So you saw the oedometer, the HCl was on the top. So oedometer, you saw that the HCl, when it came down, it was very thick. That thickness is because of this. When these hydrogen and the chlorines of the neighbors are, connected with each other. So it's just like a whole network. So this network is the even if it's a very weak attraction, it's called a very weak electrostatic attraction. It still exists, electrostatic attraction. So this still exists. That gives the texture and like the feel of HCl, how it looks like, So that's the deal with this thing. Now, dipole is not just limited to these small atoms. Dipole, this is one example. Dipole also exists in these type of molecules. Like, for example, here. Okay, you have carbon. You have these hydrogens on one side. And you have this carbon, and you have this hydrogen, and you have this carbon, and you have this hydrogen, and you have this oxygen, and this hydrogen. Remember, for the dipole, hydrogen has to attach to a more electronegative atom. That's the thing. So here's the more electronegative atom is oxygen. And in this case, what's happening? You see this part right here, oxygen and hydrogen. This is a polar bond because oxygen is holding the electron clouds towards itself. Oxygen will pull the electron clouds towards itself. Oxygen being oxygen, the electronegativity of oxygen is more than that of carbon, and carbon is more than that of hydrogen. Okay, so most electronegative is oxygen only. So yeah, this bond is also going to be a polar bond. So oxygen is, that's the nature. It's pulling the electron clouds. Hydrogen gets a delta positive charge. Now, the remaining hydrogens are connected to carbon. And there's not much of the difference between carbon and hydrogen. So I'm going to just, leave it like that. Carbon and hydrogen, there's not much difference. How much is that? Let's see, in your handout, if you see, get this out. Okay, so in your handout, if you see where is that? Okay, so hydrogen is 2.1, oxygen is 3.5, and carbon is, the electronegativity of carbon is 2.5. So electronegativity of carbon is 2.5. So what we see here is that 3.5 and 2.5 is huge, but this is like 2.1 and 2.5 is 0.4. So it's more like it's still a non-polar. I mean, that's, you know, so these are all non-polar. Okay, so one end is non-polar end, even though it's lots of carbon and hydrogen bonds, but these are non-polar, all of them. So this is a non-polar end. Okay, and this piece right here, or this whole thing, is a polar end. Polar end. And so the overall, the electron, like the electrons, like the flow or the pull of the electrons is going to be, or the polarity is going to be towards oxygen. So the pull of the electron clouds being towards, yes, this overall, this is a polar molecule. Okay, and so because of that, now this is a, there is a dipole in this molecule. So we call it, the kind of interaction this molecule will have with the other molecule would be dipole-dipole. So what does this mean? This means that this carbon, let's do this again. So carbon with the three hydrogens here, this CH2, CH, and then this CH, and then this oxygen. No, there are three carbons, sorry. This three carbons, then oxygens. So like that. So the thing is that there other forces are also going to play a role. Okay, so just keep this in mind, that the whole of the molecule, like this whole piece will be polarized. So how do I show this? This whole piece from here is polarized. There is going to be no negative charge. That's the only thing. So there is no delta negative charge here. Yet, you know, it is electron deficit in comparison, you know, to electron deficit in comparison to this. This side is more electron rich. So that is, you know, the dipole in this molecule. So we will discuss this more, you know, because other forces are also playing a role here. Okay, anyway, so let's look at the next one, which is now the dispersion. First of all, I want to clear the dispersion. Dispersion alone applies to diatomic molecules. Diatomic molecules. Dispersion alone is to diatomic molecules. So which ones are those? Diatomic molecules. Do you guys know that? Diatomic molecules, which ones? Which ones are the diatomic molecules?
Hydrogen, nitrogen, oxygen, iodide.
Yeah, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, very good, excellent. So these are the dispersion. So what is happening in this case? Okay, now here's a very interesting part. Let us say, for example, bromine. So here is this bromine, and this is another bromine. Very happily bonded together. Their octets are met. They want to make one bond. They are making one bond. Not a problem at all. Overall, the molecule is non-polar. Overall, this looks like a non-polar molecule because here's the electronegativity of bromine. Electronegativity of bromine, although bromine is highly electronegative, yet the electronegativity of bromine is what is that? Bromine is, I'm going to keep it like this, 2.8. So 2.8 minus 2.8. Remember the difference in the electronegativity. When the difference in electronegativity is equal to 0, then it is a non-polar bond. So overall, the molecule is also non-polar now. So non-polar means that there is equal. Non-polar means equal sharing of electrons. Okay, but in reality, does this happen? Does this happen in real life? No, bromine will show its true colors, to its own brother. So bromine, by nature, loves electrons, right? Loves electrons. Electronegativity of bromine is very strong, is very high. Okay, so then it shows its true colors. Bromine, it shows its true colors. And what is the true color of bromine? To pull the shared electron pairs, shared electrons. So this is a shared electron pair, okay, to pull it towards itself. Each of the bromines has their own lone pairs, but a time comes when this bromine, one of them, just changes their mind and say, hey, you know, why should I, you know, give that one electron to this guy? I want the other one also, like that, all those things. So starts thinking that. Then what happens? So this is what the story occurs with the bromine. Let's do this here. So here is this bromine and another bromine. So when it pulls the electron clouds towards itself, this one gets a delta negative charge, this one gets a delta positive charge. Okay. So when that happens, the other guy doesn't like it, because the nature of the bromine is not to get a delta positive charge. Okay. And when that happens, the other one is so upset or mad, they say, you know, the same story is happening with the other bromine also. The neighbor's bromine also, the same. All these are close together. All these bromines that are close together, the same thing is happening in their world or in their house. So one bromine is unfairly treating its you know, brother or whatever. So this bromine gets a delta positive. This one is delta negative, this one delta positive, this is delta negative, this one delta negative, this one delta positive, this one delta negative, this one delta positive, this one delta negative, this one delta positive. So this bond breaks. Eventually the bond breaks. Because it's taken that one shared electron pairs to it. Now, the moment that bond breaks, you know, can it survive? No, the new bond forms. The new bond immediately forms. The new bond, as the old bond breaks, the new one forms. And then after some times, unfortunately, the whole drama repeats again. Again, you know, that bond. So bond breaking and bond making occur at the same time. So bond breaking and bond making is occurring simultaneously. Occurs simultaneously. So we see that the bond is unstable bond pretty much. And it's just the way it is, that this is called dispersion. When there's no other choice but the electron cloud, then it's just dispersing, spreading out, right? So the moment the bromine gets a negative charge, it looks for the other bromine with a positive charge. So, you know, that's how, or the bromine with a positive charge goes to the bromine with a negative charge because it bonds that one electron. So temporarily they make an adjustment, but then again they break again. So this is continuously happening, not just with bromine and bromine, but look at this nitrogen, nitrogen, triple bonded to itself. Even that breaks. Even with the triple bond, it breaks. Oxygen, oxygen, double bond breaks. And then fluorine and Actually, it may not happen in hydrogen. I'm not sure about hydrogen, but fluorine and fluorine, because because of their electronegative nature, this happens. So, it's very interesting. We are breathing in oxygen, but the bond breaking and making is happening in oxygen all the time. Okay, so this is dispersion. So, some of the books have it this way, some books have it, some books I don't even talk about it, some books mention it, it's like dispersion, like it's, no, it's very specific. So just make a note of it, just so you have the right information. So dispersion applies to diatomic molecules. Keep that in mind. But let's look at now London dispersion, which is more specific. London dispersion is in all the molecules. Every molecule has it. That is really also dispersion, spread of the electron cloud, but the bonds don't break. That's the only difference. Dispersion alone, bonds break and the bonds are made. But in London dispersion, the bonds are just spread out, like you spread out butter on a bread, like that. So London dispersion, and these are also called van der Waals forces. Van der Waals forces. Okay, van der Waals forces. All right. Now, LDF, commonly, all the molecules have it. So if I'm asking you on the test, if I give you a few molecules and I say, okay, tell me what kind of forces are present in these molecules, then you are going to say that London dispersion 100% guaranteed, right? Other molecules, then you have to see if they are, dipole or hydrogen bonding or those things. Okay, so here we see that so here all the molecules have London dispersion forces. All right, now, okay, all the molecules have London dispersion forces. So look at now how these affect the properties of the molecules. Okay, look at these. Now I'm going to ask you, I'm giving you a project and you guys decide. First of all, you have 2 rooms. So let's do this project. And the project is 2 rooms, room number 1. And there's another room, number 2. Room number 1 is full of balls. Room number 1 is full of balls. Room number 2 is full of mattresses. Okay. Now the project is you have to clear and clean the rooms. Each room. Which one? Which room? Which room will be cleaned like or cleared faster? Room full of balls or a room full of mattresses, and why? So think about it and then tell me which ones. Room full of balls or room full of mattresses, and why? So you guys think about it while I work on these, and you can answer also in these notes in your chats. Think and write down why you think the room full of balls could be cleared faster, or a room full of mattresses could be cleared faster. What is the logistics? And if you don't have any like if you think you would need more information, a little bit more, so that also write down, doesn't matter. Okay. Yeah. So only one person has replied. Yesenia has replied, and you guys also in the class, think about it. Which one? And then just contribute your thoughts. Which one do you think would be cleared faster? And if some other insights you have, you can also share those. Okay. Matrices cause less of them fill a space, so less would have to be moved out. Okay. Okay, one person is saying about the matrices because they occupy more space, so less matrices are going to be in a room, so they could be removed. This is okay. Balls, they can roll and easily are smaller than the matrices. So Kenji is saying ball, Yesenia is saying balls, they are easier to move. So I'm not saying any answer is right or wrong yet, but it's important for you guys to, you know. What about the other people? Yes, guys. Yes. Chelsea is saying balls manageable and can be manipulated easier than the matrices. Okay. What about the rest of the students? Okay, what do you think over here, Anna, Annie? You guys, what do you think? Annie, what do you think? A room full of balls can be cleared faster, or the mattresses? Smaller and lighter, okay. And Annie, what do you think? Balls, okay. So somebody else wants to contribute here in the class? It seems like the round neopentane is more susceptible to heat than the left neopentane. Okay, Kenji. Okay, so here's the thing, guys. So the room full of balls will be cleared faster. The room, it looks like the room full of mattresses. Yes, that logic is correct, that there are going to be obviously more balls inside a room, right? More balls are going to be inside a room as compared to mattresses. The mattresses occupy like more space, and all you need to do is just maybe remove a few mattresses and compare. In comparison, that can be removed faster. But if you also have to think about it, the labor that would be need to pick up the balls versus the mattresses, you would need like more people, like, or heavier, like mattresses are heavy, so you need more people. With the balls, if you kick one or two balls, they start kicking the other balls, and then they start like moving out. So the room full of balls would be faster from that perspective, the amount of labor it is needed to do that. Now, the questions, like I told you, you can ask those questions. Yes, if the balls are made up of iron or big balls, heavy balls, then yeah, in that comparison, mattresses might just be easier, right? So it depends, what are they made up of and all those things. So the same thing, when we talk about clearing and cleaning, we are basically here looking at, the boiling point of a room. In other words, like when you take a liquid and you convert it into a gas, and then the gas escapes, so that kind of analogy. So here you see two molecules. Arrangement is different. The molecular weight is the same for both, and that weight is, or the molar mass, so this, they're made up of 5 carbons and 12 hydrogens, and their molecular weight is 75 or 72 grams per mole. So the molecular weight is the same. The only thing that is changing is the arrangement of the atoms. Here, the atoms overall, in the end, this is an electron cloud. This is an electron cloud, the whole thing. Remember, in the previous chapters, you read about the theories that it's not stable. The electron cloud, it keeps moving. So this is like a round sphere arrangement. On the other hand, if you have this one over here, this is more linear. So this is like a mattress. The first one is like a ball. The second one is like the arrangement is like a mattress. So this is more or less like, you know, that's the kind of feel the electron clouds, you know, they give like that. So when they're with each other, how do they stack? Look at this. One neopentane touching another neopentane only at like there's a small spot like here, like a little bit. So very easy to dismantle this structure. Little bit of heat and it's easy to break that structure. Don't you see like the children's ball houses? And in those children's ball houses, what happens? Little children's, they come, they kick on the balls, the structures of the balls, and the whole thing dismantles just by the kick of a small kid. Why? Because the point of contact is very small. You see this here? They're just touching each other in a very, like, very little, small part, this area right here. So the point of contact is very small in comparison to the matrices. How do they stack? Like this. Now you just have to look at it this way. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. One mattress, another mattress on top of it. So the point of contact is like every single point is touching. You see, it's all like it's more like strongly connected, these molecules. The linear ones are strongly connected. So if you look at in this case, the spread is more. The surface area is wider, more surface area, you know, so larger surface. So the point of contact of every like surface contact is very large. Okay, so because of that, the intermolecular forces are more here. Here, the intermolecular forces is less. Okay, now when we talk about what kind of intermolecular forces, these are called the London dispersion forces. London dispersion forces. Here, the London dispersion forces. But in comparison, London dispersion forces is less. Here, the London dispersion is more. Now, what is London dispersion? London dispersion is just the spread of electron clouds. Spread of electron clouds is the dispersion, disperse, spread out, right? So in this case, it manifests. If you provide heat, you will see that heat is going to bring about some change from a liquid to a gaseous state. So little bit of heat is needed. That is why the boiling point is low. Here, larger amount of heat is needed. 36 is, you have to heat it a little bit, right? More than at least 9.5. So the boiling point is more. So the more the spread, the surface area, the more the boiling point is going to be. The less the surface area, the less the boiling point is. So I'm going to do it here. Lesser surface area. And here, more surface area. So the particles, so here are the electrons are, so in other words, the intermolecular forces are more in this case. Here, the intermolecular forces are less. So what are intermolecular forces? These are the forces that bind these particles together, okay, which keep them together. So that's one thing. Next is, let's look at now hydrogen bonding. Hydrogen bonding is C and then D. So, based on this, let's see a few specific other examples I can do from the book. Dipole, hydrogen, and yeah, look at this one. Actually, I'm going to include it in here before we do the hydrogen bonding. Let's look at this other concept that relates to this, and that is the polarizability. Polarizability, or POLARIZABILITY. Now, what does that mean? Okay, even in the non-polar molecules, non-polar molecules are those molecules in which either the charges are canceling out, or pretty much where there is especially no electronegative atoms, okay, especially where there is no electronegative atoms. So in non-polar molecules with no electronegative atoms, so what's the story here? This is the thing. In these guys, temporary charges are induced. Temporary charges are induced. How? By the movement of electrons. By the movement of electrons. So this means that, here's back to this one. If you have a molecule like this, C, H, C, like all this right here, all of them are carbon-hydrogen bond. Always carbon-hydrogen bonds are like non-polar. Okay, so let's make this CH. So this is hydrogens on this end, and this is hydrogens on this end. Okay, now hydrogen, 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 and hydrogen, hydrogen, and hydrogen. Okay, so all this is a carbon-hydrogen bonds are, non-polar bonds all the time. So if they're a non-polar, what's happening? Here inside this molecule, in this arrangement, what I have drawn here is just a 2D arrangement. But in reality, they are all in 3D. The molecules are present in 3D. And this is the reason why, we have this molecular modeling labs so that you can see, in 3 dimensions how they look like. So in 3 dimensions, they are like, they have the length, they have the width, they have the height. And all this is basically, we see molecular orbital theory, you studied hybridization, you studied, especially molecular orbital theory, that the electrons are not stationary, even though they are bonded, but still the electrons move, right? Antibonding, bonding, those scenarios happen. So the electrons are all the time moving in the electron cloud. So electrons move in electron clouds. And what are these electron clouds? These electron clouds are the ones that make the bonds. Okay, so when these electrons are moving, what happens? Due to their movement, due to this movement, wherever the electrons spend more time, that site is going to be negative site. Wherever the electrons are deficit although they may be bonded, remember this anti-bonding means no electrons are going to be found there. So there is going to be it's momentarily, there is going to be like a positive charge is going to be introduced. So due to this movement, in one molecule temporarily dipole is induced. Dipole is induced. So, like cotton candies, just imagine that. You can, their shapes, yeah, their shapes and their angles are rigid, but somewhere from the outside, they're soft. So that soft piece sometimes, that can give that can be manipulated, okay, like cotton candies. Okay, so that is the polarizability. So in this thing, so let's do this again. You have 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So here, this is the electron cloud. It can momentarily, like it can be squished, in other words. And with that squishing, it can cause like one side could be a delta positive, and the other side is a delta negative, another side delta positive or negative, whatever, right? So those things can be induced. So that is like this is just a temporary charge, but it's not even like temporary charge. It's not even a real charge. It's just due to the deficit or what is it called, due to deficit of electrons. Okay, all right, so this is one piece. Now let's look at this noble gases. Look at the noble gases example that relates to the London dispersion forces also. Okay, another example of London dispersion forces. Okay, look at this. Helium, then neon, then argon, then krypton, then xenon. Okay, now helium has a freezing points. So these are the freezing point. Freeze, you take a liquid, you convert it into, you take a gas, convert it into liquid, and then freeze it to a solid. So this is very low, negative 269 degrees Celsius. Neon is negative 248 degrees Celsius. Argon is negative 189 degrees Celsius. Krypton is negative 157 degrees Celsius. And xenon is negative 111 degrees Celsius. So you see that as you go down the period, now down the group, in these, the freezing point is increasing, or you can say as you go, as you go down the group. So this is the 8th group, and you are going down, helium, neon, argon, xenon is. So this is the freezing point is very low freezing point. But here, the freezing point is comparatively higher. Not, I mean, it's not even 111, it's still very low, but it is comparatively higher freezing point. So why is that? So in other words, this will freeze quickly. Xenon will freeze in comparison quickly. Then helium does not freeze, in ordinary conditions at all, does not freeze easily. It cannot be frozen. In fact, it cannot be frozen at 1 atm. Okay. Pressure needs to be applied in order to freeze helium. Pressure needs to be high in order to freeze helium. Why is that so? Why do you think? What is happening here? Yeah. Yes, guys. What is happening? Many factors here. Many factors. Look at this. First of all, if you look at it, that the molar mass is increasing. So here, xenon versus helium and everything else in between, we see xenon has a higher molar mass. Higher molar mass means what? Heavier. This is lowest. Helium is the lowest molar mass. So when we talk about molar mass, we say, okay, this is a small molecule. So small atom. And xenon, its comparison, is a big atom. Okay, xenon is a big atom. And how do I get rid of this? No. Okay, so where do you keep? Okay, here is the, so this is a big, I don't understand why this keeps coming. Okay, big atom. So big atom means what? The spread is more. Spread of electron cloud is more. The spread of electron cloud is more. Is more. Here, the spread of electron cloud is very less. So in other words, this is, polarizability is, in short, is also called cloud distortion. Cloud distortion. Distort. Cloud distortion. Okay, so here we see that in xenon, the electron cloud can be easily distorted. So polarizability is higher. Means it can be polarized, in other words, distorted. And here, in the helium, the electron cloud cannot be easily distorted. And as a result, we see that we also have this thing, there are the electrons, the number of electrons are more. Number of electrons are more here. Here, the number of electrons are less in the case of helium. We also see the nuclear pull. Nuclear pull comparison is less. In helium, the nuclear pull is more. So the electrons don't have much freedom. Okay, so besides that, the London dispersion forces are more in xenon. And then, as you can see, they keep increasing. So it's basically, there's an increase in all these properties. When you go here, the London dispersion forces are comparatively less. So you need higher London dispersion forces. London dispersion forces are like the grease, like they are the glue that binds the atoms together or the molecules together. So this glue is more here. So I will put this here. London dispersion forces are like glue. Act like glue. Okay, so these guys are, so xenon has more glue in a way, you can say, more glue between atoms, and here less glue between atoms. So less the glue, how can you stick them, right? The only way you have to stick them is through increasing the pressure. That is why. Okay, between atoms, less glue. Okay, so this is the thing that they're going to ask in on the test, that in general, this is a trend also in the periodic table, trend in periodic table, and the same thing applies to, you know, halogens also. So I'm doing it with the noble gases, but the book is covering of the halogens. Same story with the fluorine, chlorine, bromine, iodine. The bigger the molecule, the bigger the atom is, quickly it is going to freeze. That's what it means, because there's so many electrons there, and quickly they, you know, they can the spread is more. So trend in the periodic table is that when you go in the same group, in the same group, and in the same group, when you go from top to bottom, what is increasing? We see that the decrease, there is a decrease in the freezing point. In other words, the atoms will freeze faster. Decrease in freezing point, okay, means atoms will freeze faster or quickly, okay? And there is increase in London dispersion forces, okay? So I'll just put it here that the same applies to halogens. So your book is covering about the halogens, and they're saying that, let's do this here. So you have fluorine, you have chlorine, you have bromine, and you have iodine. So as you move from top down in the same group, what you see here is that, yes, the molar mass is increasing. So molar mass increases, right, as you go from top down. And we also see the atomic radius, the size, the spread of the electron cloud also increases, right? More electron iodine has, fluorine has less. So because of that, now we have the melting point, and then we have the boiling points. So the melting points are also going to increase, and the boiling point is also going to increase. So so here it is increase. Okay. All right. So fluorine in comparison would be less than chlorine, then chlorine less than bromine, and bromine less than iodine. So just keep this in mind, that iodine will have a high boiling point. Boiling point of iodine is the highest, and the melting point of iodine is also going to be the highest. Okay. All right, so this is one thing. Next is the now last is, let's just do this, finish this off with the hydrogen bonding. Cloud, London dispersion, C. 1 second. C and D. Okay. Hydrogen bonding. Now, hydrogen bonding occurs. Hydrogen bonding occurs when hydrogen is attached to oxygen, when hydrogen is attached to nitrogen, and when hydrogen is attached to fluorine. And what is here is the rest of the molecule, we don't care. What is here is, again, for the nitrogen, we don't care. What is rest of the molecule? So R is rest of the molecule. But as far as you have the OH, as far as you have the NH, as far as you have the HF, there is going to be hydrogen bonding. So what exactly is hydrogen bonding? So here is, for example, example of water. So we have the water molecule, which is bent. Okay, water molecule is bent. So, and this is a polar bond. So we see that the oxygen, being highly electronegative, will pull the electron clouds towards itself. So oxygen will have a delta negative charge. Besides that, oxygen also has these lone pairs. Hydrogen, oxygen is not letting go of its own hydrogen. It's not letting go, but hydrogen is deficit of electrons. So hydrogen has a delta positive charge. Now, the way they are aligned, every hydrogen has a negative charge and every oxygen has a delta positive charge. So, every oxygen has a delta negative charge and hydrogen has a delta positive charge. So again, positive, negative attract each other. Besides that, the oxygen is also a philanthropist. In other words, oxygen gives its lone pairs to hydrogen, but of the neighbor. So let's look at this. Oxygen. So here is delta positive, delta positive, delta negative, lone pairs, and delta negative. Okay, so this is what happens. This oxygen, when it looks at the neighbor's hydrogen, is a hydrogen deficit, like electron deficit. So it lends its lone pairs to the neighboring hydrogen. This oxygen lends its lone pairs to its neighboring hydrogen. This oxygen lends its lone pairs to this neighboring hydrogen. Okay, and so this way, let's just do one more here. Oxygen, hydrogen, and a hydrogen. So here we see delta positive, delta negative, lone pairs, and here we have this oxygen giving its lone pairs to this hydrogen. So what is this? This is hydrogen bonding. This is hydrogen bonding. Hydrogen bonding is not the bonding between two hydrogens, but hydrogen bonding, sometimes that's what the students sometimes, get confused. They think that the hydrogen bonding is between two hydrogens. That's not how it works. No, it's the oxygen of one and the hydrogen of the other. Oxygen lending its lone pairs to the hydrogen of the other. Okay, so we see that this is a network actually. And yes, it is, these are all intermolecular forces are weak networks, but they are responsible for the properties of the substances wherever hydrogen bonding is found. Okay, properties of the substances wherever hydrogen bonding is formed. So one thing is, look at the anomalous properties of, like for example, water. Water freezes at 0 degrees and boils at 100 degrees. Water, that's one thing. That's pretty high. Boils, freezes. Okay, so freezing point is 100, is 0, and boiling point is 100 degrees Celsius. That's higher than the other elements that are connected with hydrogen in group 2. So hydrogen in group 2. So in group 2, we also have nitrogen, oxygen, and fluorine. In group 2, hydrogen. Wait a minute. Okay. hydrogen when combines with oxygen, and oxygen is in group 2, we see that, that's very high. So the boiling point and melting point, ideally you should see it like we talked about, the boiling point should increase from top to bottom, but this is the opposite. So let's look at this here first. So here is your, which is that one? Phosphorus, okay, nitrogen, oxygen, and fluorine, and nitrogen, oxygen, and fluorine. And it's a very weird kind of diagram, but let's see if we can get it. Here is okay. So 100 degrees, and then this is this is the 0 degrees, and this is negative 100 degrees, and then the bottom one is minus 200 degrees. Okay, now, and this is the second period, this is the third period, this is the fourth period, this is the fifth period, and this is the sixth period, and so forth. Okay, so normally we see here's this carbon, and all of them are less. So here is roughly carbon in the second period, and then comes the carbon in the second, then comes the sulfur in the third, and then comes the selenium in the fourth, and then comes tellurium in the fifth, and so forth. Okay, so this is a very simple, if you look at it, it's a very simple graph. So first comes, in the periodic table, you have in the second period, wait a minute, carbon, okay, silicon, carbon, so this is a period, okay, silicon, how is that? Sulfur, selenium, sulfur, selenium, tellurium. Okay, so this is, yeah, group 6. So oxygen, after that comes sulfur, after that comes selenium, and then comes tellurium. And so when hydrogen combines with them, it makes H2O. This is H2S. This is the SEH2, or H2SE. H2SE, and then the other one is H2TE. Okay, like that. So we see that this is increasing, except this oxygen. So that is creating a problem, that oxygen, when it combines with hydrogen, ideally it should have the lowest. It should have the lowest, but it has the highest. So you see, this is that line. This is that line. So that's for one thing. Next is the water. So here is our water. Then comes the HF is a little bit above 0. And then ammonia is a little bit below 0. And then this is carbon. So this is carbon, this is nitrogen, this is the fluorine, and this is with oxygen. Okay, so they are all above, like above 100 degrees Celsius. I mean, minus 100 degrees. But the rest of them are, as you go, you will see, like they will show an increase, a linear, you see them, they are going to increase like this. But these guys are like off. They should be lower in order to form a linear graph. So that's the difference here, that due to hydrogen bonding, we see that their boiling points and freezing point of water is higher than other elements in in other elements when bonded with hydrogen, in period, in like group 6 and period 2, with same thing with in group 6, in group 6. Okay, so group 6 ones, that thing, same thing applies to ammonia also. Same thing with ammonia and the HF also, same thing. They are all higher up like that. So it's not the exact diagram, but just gives you an idea that they should be lower. They should be lower. But due to hydrogen bonding, they are higher. All three of them. Okay. Okay, now that's one piece. Next is this is one piece. Next is the expansion of water. Next is the expansion. So water expands when frozen. Why? Generally, the rule is that generally all substances contract when frozen. All substances contract. They lose their size, they contract when frozen. Okay, but water expands when frozen, and that is due to hydrogen bonding. Now, what is this happening? Due to hydrogen bonding. So what does this mean? This means that the water expands, that's one thing. And second thing also, that the water is lighter. No, sorry, the ice is lighter. So all this is related to that. So ice is lighter, like density is lower. Okay, ice is lighter than water. Therefore, it floats. So generally, the general rule is that generally solids, all solids have higher density. But here we see that the water has, in a solid form, has a lower density. So generally solids have higher density. Generally, not all of them, obviously, exceptions are there. Generally, solids have higher density than liquids. So for the most part, solids will sink. But water, ice is floating. So why? Again, due to hydrogen bonding. Now how? What does this mean? So here's the thing, that they haven't drawn this diagram in your book, but if you can get that, how do they, think about it? Icicles are like those, snowflakes, right? Those snowflakes. And if you see, most of them are like still hexagonal shapes, but the shapes are different. The shapes of, there's no two snowflakes are ever going to have the same shape. But here's the thing, water molecules, when they form hydrogen bonding, they form it. Hydrogen bonding occurs at an angle. Hydrogen bonds are formed at an angle. Are formed at an angle. At certain distance from each other. Okay, that is important. So it's because this happens because water molecule is bent. So it has to accommodate all those things, angle and distances, all those things. Water molecule is bent and it's very rigid. So this is why, they form these hexagonal shapes. So fine, this is one water molecule, this is another one, this is another one, this is another one, this is another one, and another one. And they form this very weak hydrogen bonding. Okay, so this is very weak. This is the hydrogen bonding between these six of them. So six hydrogen bond, six molecules, they bond the hydrogen bonding among themselves and form this shape, more or less this type of shape. So six molecules, they make, these shapes of flow snowflakes, in which hydrogen bonding is playing a role. But keep this in mind, that fine, we understand that because of this, to accommodate hydrogen bonding, the ice will be expanding. The water molecules, they expand to accommodate hydrogen bonding. Molecules, they space out. Molecules space out. And when they space out, what happens? They need space, right? So that space out means they spread out. So when they spread out, what happens? So the ice expands. Water in its solid form is expanded, expands, or is more than the water. Spread is more, okay? But at the same time, why is it lighter? When this is happening, what happens is that the air gets trapped in. So this part you see in the middle is air. Air gets trapped in. So when it's expanding, ice expands, and when it is spreading out, or when the molecules are spreading out, when molecules, hydrogen bonding is always there. When molecules spread out, air gets trapped. Air is trapped, and this air is what makes the ice lighter. Therefore, ice is less dense. Density is less. It's like it's floating. That's why it floats. Okay, this because of air, the ice floats. Air trapped inside these hydrogen bonded molecules. Okay. Now the same thing applies to ammonia. Same thing applies to those things. But let's just finish this here. Some of the examples for practice. Examples. And these examples are, like, for example, they can ask you, this guy, okay, very interesting example, one here. So you have, okay, here is the water, oxygen, and here, okay, polar molecule. And here is C6H14. So CH3, CH2, CH3, sorry, CH2, CH2, CH2. So 1, 2, 3, 4, 5, and CH3. Okay. So this one is C6H14, huge molecule, right? Huge molecule, C6H14. The boiling point of this guy is 69 degrees Celsius only. This one is just H2O. But the boiling point is 100 degrees Celsius. Why is this more? Why? Yeah. So you are just going to write down all the intermolecular forces. In this case, London dispersion forces is present in both of them. Both of them will have London dispersion forces. But water will also have dipole-dipole. Remember, dipole is what? Wherever there is one side is a negatively charged side and the other side is a positively charged side. So this also has a dipole-dipole. So dipole-dipole. And the third thing that is coming in water is the hydrogen bonding. The other molecule is huge spread out, but no hydrogen bonding. no dipole dipole. So more intermolecular forces here. And this has only one intermolecular forces less. That is why the boiling point is more. So it's not all the time that the higher the molecular weight is going to be, then the higher the the boiling point is going to be. It's not necessarily that. You also have to look at like other things. Okay. So that's one piece. Next is look at the second example. So in other words, when the boiling point is less, this is also called more volatile. So question can be asked, tell which one is more volatile. So the ones that has less intermolecular forces is going to be evaporate fast. Okay, the one that evaporates fast. Okay. Let's look at another example of this guy. Why? Look at this one. Okay, very interesting. 1, 2, 3. Okay, 1 CH3 CH2 CH2. Okay, 1, 2 butanol. 1, 2, 3, 4 CH2 and OH. And the other one, now look at this. 1, 2, 3, 4. The other one is CH3 C H2, then C OH, this is H, and here is CH3. Okay, another short way of writing this is 1, 2, 3, 1, 2, 3, 4, and OH. This guy is written as 1, 2, 3, and OH. Line diagrams. So this is a line diagram. So that's organic chemistry. This is also a line diagram. So you guys don't need to get this, but just to give you an idea, line diagram. So tell me, the question is, which one will have a higher boiling point? Both of them have the molecular formula of C4H10O. Both of them like the same number of carbon, hydrogen, and oxygens. But which one will have a higher boiling point? Which one will have a higher boiling point? This one or this one? Yes. A or B? Which one? Higher boiling point is of which one? A and B. We covered this a little bit. Both of them will have hydrogen bonding, right? Both of them have London dispersion. London dispersion is in both of them. London dispersion here, London dispersion here. This one also has a dipole because one end is polar, the other is not. So this one also has a dipole. Dipole. This one also has hydrogen bonding. This one also has hydrogen bonding. So now what's the deal? Which one will have more boiling point, higher boiling point? Yes. Yes, guys, come on in the class. Because it is more linear, very good. Kenji, seems like a round neopentane is more susceptible to heat than the flat neopentane. Very good. Chelsea got it. Balls. So same thing. So here we have same story. The spread. Look at this. Oh, sorry. Look at the spread of the electron cloud. Here it's spread out. So like a mattress. This is like a mattress. This is like a ball. This is still like, you know, like more like a smaller ball, you can say at the worst. Or this is like a, you know, squished ball or whatever. But this is like that. So this is still definitely a mattress. This is more like this. So the ball versus mattress analogy. So keep that picture in mind, that the boiling point of A is going to be higher than the boiling point of B. Ball, no, this is mattress. Looks like mattress. So looks like mattress. And this one looks like a ball. All right. All right. So that's the only thing now. And I actually want to just finish off one last piece, because then next time you come, we start with the phase change of state and phase diagrams. So that is now the surface tension. Surface tension. What is surface tension? Surface tension. Surface tension. So this was 4. Okay, all these forces take part in, so 4. Okay, surface tension. So when we say tension, that means there's some kind of a pull on the surface happening. So here's the thing, because we talk about the surface. So here is the top part. Inside a liquid, what's happening here? These are the particles inside the liquid, and these particles that are inside are also, connected in a network with London dispersion forces, all this. So the interesting part is that the inner particles are surrounded by other particles more, so they are being pulled in all the directions, whereas the particles that are on the top are only being pulled from one side. The top side, they're not being pulled. The ones that are at the bottom are, are being pulled from all the sides. So the pull is more, of the middle ones, but the top ones, they are being pulled less. So what happens is that the top particles, let me write this down, the top particles experience less pull. Okay, less pull, or less, less pull of, that's the intermolecular forces. So what happens then? Why are they pulling these? So why these? Because what happens is the liquids particles, liquid particles in liquids, particles resist increase in surface area, increase in surface area. And because of that, they, remember, these are like, they're round. Many of the liquids will be rounded like this. So if this is the surface here, so the top ones are obviously not very, so let me just make a few of them here also. So here, they are pulled from the sides, from all the directions. So the ones from the side, they're curved. These guys are getting curved. And this curve is causing that due to surface tension, it's all like, it's curved, because the whole idea is to get the smallest surface area. And that round or a sphere has the lowest surface area. So that's geometry, lowest surface area. So that is why all liquids, they curve to some extent, depending, nature of the liquids also. Lowest surface area. So nature of the liquids is to form beads. The process of surface tension is basically beading. They form beads, beading. And this beading is also called the droplets. If you've seen it, oils form droplets, right? Every liquid, it will form droplets, no matter what, okay? So the more polar liquids are, the more the surface tension is going to be, the more the particles are going to attract each other, okay? So more polar liquids will have, more polar liquids, surface tension is very high. So that means the beading is going to be more. Now, what happens is that there is a product called Rain-X. I don't know if you guys have seen this. Rain-X actually is used to clean the windshield in the when it's raining. So clear the windshield rather. So the water doesn't bead. So prevents the beading of water on the windshield. So Rain-X prevents beading of water, like droplets, right? Water on windshields in the in rains. Windshields of cars in rainy season, when it's raining, so that you can see it clear. Otherwise, water droplets keep sticking to the glass surface. Glass is polar, water is polar. It's a very bad state. So that's the surface tension. Now let's look at a capillary action. 4, 5. So keep this in mind that more polar, look at the molecule. If it is very polar, definitely there is going to be very strong surface tension. So look at that. If you're given something that, which one, like for example, if you're given something like CH3, CH2OH will have a higher surface tension than CH3, CH2, CH3. Because of this is more polar hydrogen bonding. So will more stick to each other. Okay, next is capillary action. Capillary action happens in the capillary tubes, and not just in the capillary tubes, the glass capillary tubes, but in nature also. We see in the plants, the water moves up the veins through the capillary action. Okay, so two types of forces occur in the capillary action. One is the cohesive force, and the other is adhesive. Okay, what is a cohesive force? Cohesive force is among the liquid molecules. Among. So this is among liquid molecules. They stick to each other. Okay. But adhesive is between the liquid molecules and the container. Adhesive, like a glue. Between liquid molecules and the container. Okay, so what does it look like? So here's the thing. If you have this guy over here, open at both the ends, this is a glass tube, open at both the ends, and you put it in a container, and you have a liquid here. So the liquid is going to move up the capillary tube all the way up, and it comes, at a certain level, it stops, but it does get, and it stays there. It stays there. So the fact that more polar the liquids are, once again, more polar liquids, the capillary action is going to be fast. More polar liquids, more capillary action. Okay, the faster they move up the capillary tube, more capillary action, or the rise in the capillary tube is more. Okay, so they rise up more. Why? Because they stick to each other. There is hydrogen bonding, and there is hydrogen bonding. There's London dispersion, dipole, dipole. For all polar, it's going to be there, and hydrogen bonding. So all these are present in mostly in polar molecules. So think about it. In these polar molecules, the intermolecular forces are higher. So that is why they will pull each other up. Besides that, think about it. The polar, remember, like dissolve like. So polar and polar stick to each other. So glass is polar. Glass of capillary is polar, and the liquid is polar. So this liquid that is polar is going to stick to the glass strongly. Okay, so polar and polar attract. Okay, that is why oil doesn't move up the capillary tube, but water will. Quickly, the water moves up very fast, because water loves glass. I mean, water really loves glass. Because glass is polar, right? So just keep this in mind. Okay, the last piece is the viscosity. Viscosity. Viscosity is what? Thickness. This is just thick, 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 like oil, like creams, like grease, like lotions. So it's thickness. Now, what causes that thickness? In other words, viscosity also means that thickness is resistance to flow. Resistance to flow. Okay, so we see that in this resistance to flow, what do we see? For example, you have here hydrogen, carbon, OH. Carbon, OH. Hydrogen. Carbon, hydrogen, and OH. So fine, all these OH, OH, OH is definitely going to be hydrogen bonding here. Okay, because of this OH, the 3 OH in one side, this is definitely this hydrogen bonding causes hydrogen bonding here. Hydrogen bonding makes, this is glycerol. So hydrogen bonding makes this viscous. Viscous means very thick to touch, right? Besides this is one example if there is lots of hydrogen bonding. But if there's no hydrogen bonding, then what? So look at this, CH3, and then you have CH2, and then CH2 and whatever, and then there is CH3. Now, if there are now as many number of, keep this in mind that this is n number. Now, if this n number of CH2 is from 3 to 8, okay, 3 to 8, like gasoline. So gasoline, we have all filled gas in the car, right? So gasoline, less viscous. Yeah, I mean, if you've ever touched the gasoline, it's, it's like that. But if the number is from 20 to 25, okay, then it is such as in grease, such as in oils, such as in creams, right? Such as also in butter, okay? Those things, lotions. So they are all, you've seen it, very greasy. So they are very viscous. That makes it very viscous. The spread is not that much. Okay, guys? All right, so there's so many details. But that just finishes. And we have just 2 more things to go when you come next time. And those 2 things are change of state and the phase diagrams. Definitely, those are going to be on the test. So anyone has any questions? All good? All right. So let's just wrap up now. I'm going to close the meeting and you guys can take a break. Today's lab is not very big. You just have to do a checkout and, just make some molecules, see them in 3D, how they look like, and that's it. Okay. All right. Okay, guys. Bye. I'm stopping the recording now.